Thank you. So I'm going to talk about some joint work we've done together with Raman and Kristen. Our motivation for this work is this observation that humans are getting good at responding to algorithmic systems in a way that benefits them, but not necessarily the firm implementing those algorithms. And examples range from people making thousands of dollars by gaming the reward app of a bike sharing system, gaming credit scoring systems, triggering search pricing by coordination, responding to resume scanning algorithms, many examples like that. And motivated by this, there's this line of literature on a strategic machine learning or machine learning with data that behaves. So if you're a firm and you know that people are going to respond to your system, you might preemptively change the way you're going to make decisions in a way that prevents gaming and potentially induces desirable behavior. But one thing we observed in this literature is that there was an assumption that people have very good understanding of algorithms and can use that understanding to best respond to them. Or in other words, it is an assumption that people are behaving rationally, they're fully rational when they're giving algorithmic information. We wanted to bring in a different aspect to this and say, what if people do have the information, but they have behavioral biases when they're responding to that information, trying to game the system? This is part of the larger literature of understanding impacts of human biases and cognitive limitations in human-AI interaction. It is also related to this literature on a strategic classification with opacity, where the setting is that people cannot best respond to an algorithm just because they don't have full information about it, because the algorithm is being opaque. In our setting, I want to emphasize that we assume that the algorithm is actually telling you exactly how it's making its decisions. It's being fully transparent. It's just that people have limitations in digesting that information. And specifically, the hypothesis that we make is that people have prospect theoretic biases. This is a model from behavioral game theory. In its original form, it says that people tend to overweigh low probability events, but underweigh high probability events. And we said, what happens if we assume people have the same type of bias in interpreting feature weights in a classifier? So what if they are placing too much value on low importance features, but placing not enough value on the high importance ones? So with this hypothesis, we developed an analytical model to see what would be the equilibrium that comes up in the principal agent game. And we also conducted some survey experiments to see if this type of bias actually might exist. So let me start with the analytical stuff. It is extending the classical strategic classification model from the rational agents to the behavioral agents. The classical model is a principal agent problem. The agents are the followers. They see the classifier announced by the firm. These are some weights, some feature weights theta and a threshold theta 0. Knowing that the agents can exert costly effort subject to a budget constraint with the hope of getting positive classification. The firm knows this, so in not knowing that the agents are going to interact with it this way, it is going to announce a threshold that tries to minimize the gaming. If you wanted to illustrate this in a 2D feature space, you see the agents are spread out over there. Positively labeled agents are blue, negative ones are, or truly qualified agents are blue, truly negatively qualified agents are red. And then the classifier announces, or the firm announces a solid blue line. And then you see a strip of agents there who have movements. Those are the ones who can afford to manipulate this algorithm. Now, the variation of this that we have is, again, a principal agent problem very similar. The difference is that the principal is announcing that the classifier is theta, but people are mishearing it or misunderstanding it as W theta, where W is those behavioral biases, the prospect theoretic biases. If we wanted to illustrate this, again, the classifier announced is a solid blue line, but people hear it wrong. They hear the tilted one, which is the solid red line. And now you can see there is a difference in the way people are responding to this algorithm when their behavior compared to if they had been rational. So the first step that we take is actually compare the responses of behavioral agents with the rational counterparts. We see that depending on the starting location of agents in the feature space, they might be eventually over-investing or under-investing compared to the rational counterparts. And this has implications for the firm in terms of what classifier they choose, how much gaming they experience, and also their overall utility at the equilibrium of this game. The takeaway that I want to mention from this analysis is from the firm's perspective, at equilibrium, you would have generally, most of the time, you would have higher utility if you had these behaviorally bounded agents trying to game your system, because they're bad at solving the optimization problem, the best response. So they're best responding suboptimally, and therefore you're experiencing less gaming. But the surprising result, or the more surprising observation, is that this is not a universal result, meaning that there exist problem settings in which the firm would prefer having these fully rational agents trying to game its system rather than having the bounded rationality ones. The reason for this is if you look at the region in which people are gaming the algorithm, you have both originally qualified or positive qualification agents and also negative qualification agents trying to game the system. Depending on how the threshold is flipped or the way it is tilted, you might lose more of these qualified agents who were gaming your system successfully. You don't mind that, right? Eventually, they're not going to hurt your firm even if they game it, but you might be getting more of the unqualified agents still successfully gaming your algorithm. So if the threshold had not flipped, you would have a better balance. So the takeaway from this is that the fact that users have behavioral responses rather than rational ones has implications for the firm, both in the way it designs its classifier and also in the ultimate utility it is hoping to achieve. But we wanted to see if people actually exhibit the type of bias that we assumed. So we conducted some survey experiments. This is on the Prolific platform. We gave our participants the task of helping a friend spend a limited amount of time, 10 hours, to improve their application material so that they would be selected by an algorithm for a job interview. And we allocated our participants across 4 experimental conditions. They differed in whether we told them your friend has 2 or 4 features they can change, and whether those features would eventually be weighed equally or in an unbalanced way by the algorithm. And so we saw that, as you might expect, participants do respond suboptimally, meaning that they don't optimally allocate those 10 hours on improving these tasks depending on which experimental condition they're assigned to. They get worse at it as the number of features increases and as the features become unbalanced. But the good thing for us was that the way these responses are suboptimal aligns to a good extent with the model that we have proposed, in that you can interpret the way people are misallocating the time as them placing too much weight on the low importance features and not placing enough weight on the high importance ones. So this can be interpreted as consistent with our assumed model. But as you might expect, there are also some ways of responding, some cognitive biases that people are exhibiting that is not necessarily the model that we considered. One example of that is that we conducted another set of experiments, now with a different context. Instead of asking people to help their friend make a decision about how to allocate their time for a job application, for a job interview, we asked them, how would you help your friend allocate their time to improve health metrics for an upcoming medical test. And this was more unfamiliar. We saw that people still mismanage the way they allocate the time, but the suboptimality has gone down. So our current belief about why this happens is that people bring in their own preconceived notions of what features are important in the job application scenario and potentially respond given their own pre-existing biases. So despite the explanations of the algorithm that has been given to them. All right, so I'm going to wrap up. In summary, we have a new model of a strategic classification, which instead of assuming that people are fully rational, assumes that they have these behavioral biases when responding to knowledge about the algorithm. We show that this has implications for the firm. Ultimately, these biases may benefit or may even hurt the firm. Anything can happen. Our survey experiments can be interpreted as being very well aligned with this model of feature weight misperception, but there exist other forms of cognitive biases that we're observing as well. And motivated by this, we believe there is room for exploring other forms of cognitive and behavioral biases when we're studying these strategic human-machine interactions. And this can be done both in theory and in terms of user studies. We also believe this can inform the design of explainability methods. So we see that these feature weight explanations, people are not very good at taking them in, these bar plots. And are there ways of offering explanations to users that are more understandable for them and that can help them surpass these potential forms of biases? All right, I'll stop with that. Thank you.